When Google set out to win the nearest neighbor benchmarks, it didn't just make search faster. It rethought what compression should even optimize for. The result is ScaNN, short for Scalable Nearest Neighbors, a high-performance vector search library whose headline idea sounds subtle but changes everything about ranking quality. Let's dig into why weighting error differently turns out to matter so much, and how the whole search pipeline is built around that one insight. Start with the thing ScaNN questions. When you compress a vector to save memory, what exactly should you try to preserve? Standard quantization tries to reconstruct each vector as faithfully as possible, minimizing the raw error evenly in every direction. It treats a small mistake pointing one way as just as bad as the same mistake pointing another way. That sounds perfectly reasonable, but it quietly ignores what these vectors are actually used for, which is comparing them to a query and sorting the results. ScaNN reframes the goal around the ranking. For inner product search, an error along the direction of the vector distorts the score far more than an error perpendicular to it. So ScaNN's loss deliberately weights that parallel error more heavily, preserving the inner products that decide who ranks on top. That insight sits inside a full search pipeline. Follow a single query through the 4 stages ScaNN runs. Partition comes first. ScaNN splits the whole dataset into groups ahead of time. Then, for an incoming query, it only opens the partitions that look relevant. Right away, most of the database is skipped, which is what keeps things fast. Scoring comes next. Inside those partitions, ScaNN measures candidates using its anisotropic quantized vectors, and it does this with heavily optimized hardware instructions that crunch many candidates in parallel. This is the pass where all that care about preserving inner products finally pays off in ranking quality, because the compressed scores still order the results correctly. Shortlisting narrows things down. From all the scored candidates, ScaNN keeps just the most promising handful, the ones that look like genuine top contenders. Everything else gets dropped, so the expensive final step only runs on a tiny set. Then comes the exact re-rank that finishes the job. On that short list, ScaNN computes true scores with the full uncompressed vectors, fixing any small distortions the compression introduced. You get approximate speed on the vast majority, and exact precision right where it counts on the candidates that actually decide the answer. Now, why did this design end up topping the benchmarks? 3 ideas do the work. First, anisotropic quantization. By caring more about error along the vector's direction, ScaNN keeps the inner products that drive ranking intact, so its compressed vectors rank almost as well as the full precision originals while using far less memory. That is the piece nobody else was optimizing for. Second, the partition then score then re-rank pipeline. Cheap approximate passes throw out the obvious losers, and only a tiny shortlist gets the exact treatment. That staged approach spends effort exactly where accuracy matters and nowhere else. Third, the payoff. Putting those together, ScaNN delivered state-of-the-art speed and accuracy on public nearest neighbor benchmarks, sitting right at the frontier of the speed versus accuracy curve, which is exactly why it shows up in serious production retrieval systems today. Alright, let's gather the key points together. ScaNN is Google's high-performance vector search library, known for winning nearest neighbor benchmarks. Its core idea is anisotropic quantization, weighting error along the vector's direction to preserve the inner products that decide ranking. It partitions the data, scores candidates fast with compressed vectors, then re-ranks a short list exactly. Optimizing compression for the ranking, not raw reconstruction, is what buys its speed and accuracy. Curious about more retrieval and machine learning topics broken down simply? You'll find them waiting at Standarity.com.